Hello everybody, and in this video I'm going to be tackling 3 f equals ma problems, hopefully in not too much time. They are all related. As we can see here, it says the following information applies for questions 20, 21, and 22. So we have a particle of mass m, here I'll draw a quick sketch, moving at velocity v0, and it collides with a particle of mass capital M, which is originally at rest. Then we define the fractional momentum transfer, F, is the absolute value of the final momentum of m divided by the initial momentum of m, of small m. So for question 20, it says, if the collision is completely inelastic, which means the two particles stick together, under what condition will the fractional momentum transfer between the objects be a maximum? So we know that if in any collision, right, momentum is conserved. So what that tells us is that small m v0 is equal to basically the initial momentum will be equal to small m v1 plus big M v2 if we say that these are the velocities of the two respective objects. And now, so what does that tell us, right? So we know that if it's inelastic, we will have mass m, or little m and big M, stuck together moving at the same velocity, right? So in particular, we know that v1 is equal to v2. So we can, so I'll just call that v. So we know that m v0 is equal to v times m plus big M. And this is the momentum of the system, right? Because the momentum of big M is 0 initially. But the momentum of big M after the collision is just big M v. So we want to know the ratio here of big M v divided by m v naught, by little m. That's a little m. So we can use this equality here, and we'll see that the v's cancel out, and we just get that m over m plus m is this is our fractional momentum transfer. Now we see that if we were to divide the top and bottom by m, we would just be left with something in the form of 1 over x plus 1. And that would imply that obviously the bigger that x got, and x is little m divided by big M, the bigger x got, the smaller f would be. And we want f to be at a maximum. So we want m over capital M to be very small. Then f will approach 1. So little m divided by big M needs to be very small, which in our case is option A, right? It's very small. Next, we want to consider if the collision is perfectly elastic, which means that kinetic energy is conserved. Then we want to find what the maximum possible fractional momentum transfer is. So now we have the same equation here, right? mv0 is equal to v times m plus capital M, because momentum is still conserved. Well, actually, no, that's not true. Sorry. So, but we have this one, right? mv naught is equal to m v1 plus big M v2. And we also have 1/2 m v naught squared is equal to the sum of the kinetic energy. So this is conservation of momentum, and this is conservation of kinetic energy. So we have that these two equations are simultaneously true. Now here we can just cancel out the 1/2 for convenience sake. And that makes this a lot simpler. Now I'm going to introduce a variable here to make things a little easier, and that will be capital M divided by little m, so that I can just divide out by little m in all of these equations and just be left with an x here and an x here. Whew, okay, so now we see that if we plug v0 into this equation and we expand, we'll get this equation after so the v1 squared will cancel. And here we see that both sides are divisible by x and v2. And so we can reduce power of v2 and get rid of x's here. So we get something very simple. Now let's look at what our f is, right? Our f is big M v1 over little m v0. Or sorry, this should be a v2. v2, which is x v2 over v0. So we want to know what v2 over v0 is. Well, here we have, we can easily solve for v2 over v1. And we see here that if I were to divide this entire equation by v0, we would get 1 was equal to v1 over v0 plus x v2 over v0. And so we can substitute v1 here. So if I were to divide this whole thing by 2 and get a 1/2 here, then we can plug in what v1 is, and everything will be divisible by v2 over v0, basically, or we can factor that out. And what's left will be 1/2 minus x over 2 plus x, which is 1/2 plus x over 2. And this is equal to 1, so we can just solve for v2 over v0 and then multiply by x to get f, right? So here we have f will be 2x over x plus 1. And so now, again, we're just looking at what the minimum of this will be. And in our case, again, as x goes to 0, we will, or not as x goes to 0, but, or no, other way around. So as x goes to infinity, this will approach 2. So the maximum f will be 2. Now onto problem number 22, and we're basically considering the previous example, but we are looking for the fractional energy transfer. So this is basically the same thing as we were considering before, but now we have both of the velocities squared. So v2 over v0 squared. And so, of course, we already solved for what this was. And so we have 4x over x plus 1 squared. And we want to find the maximum of this, or the conditions for the maximum. And let me think. So now, since we're dealing with positive quantities here, specifically positive x values, what we can do here is apply the AMGM inequality on X. Um, Now I'm doing this as to provide a non-calculus solution, because obviously you could find the derivative of this and set it equal to 0, find the maximum. But here we can apply AMGM. So AMGM basically states that the arithmetic mean of two numbers is greater than or equal to the geometric mean. And for our case, that means that x plus 1 is greater than or equal to 2 times the square root of x. Now this is also true if you were to, um, if you subtracted 2 square root of x on both sides, you would be able to factor this and you would get a square was greater than 0. So you don't really need AMGM for this, but that's a more technical term. And so if I were to replace x plus 1 with something smaller, if I make the denominator smaller, then I'm making the entire fraction bigger. So this will be greater than or equal to. Now, if I square 2 square root of x, I'm obviously just going to get 4x. So you see that f is greater than or equal to 1. But in particular, we have equality when this is equality. And this is equality when x is equal to 1. But what is x? X is equal to big M over little m. So the answer to this question is just C, little m is equal to big M. So anyway, that wraps up this video. 3 birds, 1 stone. And I hopefully made this, or I gladly made this non-calculus, even though my other video on problem number 25 did involve calculus. But I hope you enjoyed this solution. Thank you for watching, and I'll see you in my other videos.